Hello, Chem 30 students. So today we are looking at naming carboxylic acids and esters. So curricular outcomes pretty much the same as everything we've looked at up until now, just being able to name and draw the structures. And with the carboxylic acids and esters, we have a different functional group that makes them into carboxylic acids and esters. And so you just need to be able to recognize those linkages given the structural formula and identify the compound from that. And then again, just like we saw in previous lessons, you should be able to identify a little bit of the physical properties in terms of like boiling points and solubility. So specifically with the carboxylic acids, that's going to be something that we're going to be looking at in this lesson. So carboxylic acids are, or a carboxylic acid rather, is an organic compound that contains something called a carboxyl group. And so the way that we represent that is, like if we have a condensed structural formula, it's with this COOH. So you'll see that quite a bit. And if you look at any of your acids on your acid chart in your data booklet, you'll also see that that form comes up a bit because that's an organic acid. So for example, if we look on here, oxalic acid, you can see it has the COOH there. Citric acid here again with the COOH. Some pretty common ones. Lactic acid, you might know that from the fact that it can accumulate in your muscles when you're doing anaerobic exercise. So we see that quite a bit when we work with acids. Now, what is a carboxyl group? Well, basically here you can see the whole carboxyl group, which is actually made out of two smaller functional groups. So a carbonyl group and a hydroxyl group. The carbonyl group is just the carbon that's double bonded to an oxygen. And the hydroxyl we looked at when we were looking at alcohols, which is that OH group, or the hydroxide polyatomic ion attached to the end. Now, when you have both of these together, we call it a carboxyl group. So they've kind of combined the words carbonyl and hydroxyl there. So because this uses up 3 out of the 4 available bonds on a carbon, you'll always find this carboxyl group at the end of a chain. So if you're looking at a hydrocarbon chain, this will always be at the end. The only exception to that would be if you have methanoic acid, in which case you would just have a hydrogen here, right? But usually there's going to be a chain of other carbons going off in the other direction there. But that's the only other available bond for the carbon. Just a quick note here, carboxylic acids can still be saturated because the whole chain coming off of here still has the potential to be saturated, right? The double bond isn't between two carbons, it's just between this carbon and the oxygen. Now, when you guys get into testing, one of the things you should be able to do is identify some of the physical property tests that you would be able to do to identify whether a certain organic compound was for example, a carboxylic acid or an alcohol or something like that. Now, carboxylic acids are really nice because they have multiple tests that you could do to identify them. One of the things is that because they are an acid, they're associated with a sour taste. So even though obviously we wouldn't say if you're in the lab and you're not sure what something is, do a taste. But you can still, in a test situation, if you were asked for a physical property test that you could do with a carboxylic acid, one of them could be identifying a sour taste. Another one that you could also do is because they're acids, they're going to have a low pH, and so they're going to turn litmus red. So you could always do a pH test. On a test, you could either say, they'll have a low pH, or you could say, try a litmus test, and they should turn litmus red. The other thing is carboxylic acids are polar molecules, so that means that they dissolve in water. So just like with the other compounds we looked at, the larger the molecule is, the less we're going to see the polarity affecting the properties of the molecules. So basically that means if you have large molecules, we're not going to see as much solubility as we would for a short chain carboxylic acid. And we're going to see the same thing with boiling point. So the bigger the compound is, the less that those intermolecular forces are going to be strong enough to hold them together really tightly. So that will affect the boiling point a little bit. But in general, we do say that carboxylic acids have a really high boiling point because they have the hydrogen bonding in that hydroxyl group. So if we look at down here, we have a guide to common fruit acids, and you're asked to find all the carboxyl groups in fruit acids. This is a really good skill to have because a lot of times, we'll try some practice examples of this at the end, but a lot of times this is something that you're asked to do on diplomas and tests where you really have to make sure you're confident in your identification of those groups, especially when we get into esters in the next part of this. We'll cover that in this lesson as well. You just have to really make sure that you're familiar with that. So for example, and with carboxylic acids, one of the big things is be able to differentiate between a carboxylic acid and an alcohol because they both have that hydroxyl group in them. So if we look at citric acid here, which is the acid that's you're probably pretty familiar with, you've probably heard of it. It's in most of the sour kind of fruits like lemons, limes, oranges, but also things like pineapple and strawberry. So if we look at this structure, if you want, maybe just pause the video right now and see if you can go through these and see if you can find all the carboxylic acid groups or carbonyl groups, or sorry, carboxyl groups rather. And then you can hit play and see if you got them all. So in this first one here, we have a carbon double bonded to an oxygen with a hydroxyl group off of it as well. And so that would be one right there. Carbon with two hydrogens is not it. Carbon with a hydroxyl group, but because it doesn't have that double bonded oxygen, it's not a carboxyl group. This is an alcohol group here, okay? Here we have a carbon double bonded oxygen, and off the same carbon we have that hydroxyl group. So together this makes our carboxyl group. So that's the second one. And same thing over here. We have a carbon double bonded oxygen and a hydroxyl group. In this one here, we have, this carbon has double bonded oxygen and a hydroxyl group, so that makes it a carboxyl group. Over here, again, we see this is an alcohol group because there's no double bonded oxygen, just the hydroxyl. But here, again, we have a carboxyl group. Last one over here, same thing. And you can probably tell what the pattern is here. Like we mentioned in the previous slide, carboxyl groups are always found at the ends of molecules or on like side branches at the end of the side branch as well. Okay, and that's just because there's so many bonds being taken up with the double bonded oxygen and the hydroxyl group. Okay, so in terms of naming carboxylic acids, if you have any side branches or groups off the main chain, your prefix is going to give that. Now, technically, you shouldn't have more than one functional group in a carboxylic acid, so you probably won't have to worry about this in any of your questions, for sure not in a test. The root is always going to indicate the number of carbons in the longest continuous chain that includes the carbon in the carboxyl group, okay? And that carbon that has the carboxyl group in it is always numbered carbon number 1. The suffix for your carboxylic acid, so for example, if we had propane, like if we had 3 carbons as the root, we drop off the E and replace it with oic acid, so it would be propanoic acid instead of propane, okay? Let's see. So here you can see an example of like a side chain as well as the functional group here. So we have on the main chain, we have 1, 2, 3, 4 carbons. Over here we see our carboxyl group. So we're going to number that carbon number 1, 2, 3, 4. So that means we have butanoic acid. So this is telling us to change the ending to butanoic acid. But on carbon 3 we have a methyl group. So it's going to be 3-methyl butanoic acid. Okay. Oh, and the other thing to be aware of is just when you're writing the condensed structural formula, sometimes you'll see the carboxyl group written as COOH, but if this group was on the left side, because the condensed structural formula is still trying to communicate the actual physical structure, it would be written the opposite way. It would be written HOOC, okay? Because if you think about how the bonding would go if you were going in this way, you would have the carbon, and you'd have the double bonded oxygen, and then you'd have the oxygen and the hydrogen, and then whatever else you have going on in the group here, like CH2, right, going on like that. So when it's on the left side of the molecule, this carboxyl group, it's HOOC and then the rest of the chain. Whereas over here, you would have this structure reversed. So it would be like a mirror image of this. So this would be going off to the right side. So it would be COOH. And that's why we write it in these two different ways for the condensed structural formula. So let's try an example of naming carboxylic acids here. So over here we can see we have a carbon double bonded to an oxygen and single bonded to a hydroxide group. Hydroxyl group. So this here is telling us that we have a carbonic acid, carboxylic. Okay, and so now we just need to figure out how long is our parent chain. So don't forget to include this carbon is carbon number 1, then we have carbon number 2, carbon number 3, carbon number 4, and carbon number 5. So we know that pent is going to be the name for our root, so it's going to be pentanoic acid. But on carbon 3 we have a single carbon being branched off, so that's a methyl. So we have 3-methyl, and then like we just said, we have 5 carbons on the parent chain, so it's pentanoic acid. Okay, so there's the name for that one. Next one here, again, we find our carboxyl group is COOH, so that has to be carbon number 1. And then looking for the longest chain branching off of there, 1, 2, 3, 4, 5. I don't know, it could be 6 or 6, it doesn't really matter, but I'm going to stick with the straight chain. 4, 5, 6. Either way, you're still going to have a methyl group off of carbon 5 there. So we can see we have a methyl group here and a methyl group there. So we're going to have dimethyl. And then off of carbon 2, we have an ethyl group. Okay. So that means we're going to have, remember, you want to name your lower alphabetical group first. So we're going to have 2-ethyl dash, and then our methyl groups are on carbon 4 and 5, so 4, 5 dash dimethyl. And then our parent chain is 6 carbons long, so that's hexanoic acid because of our carboxylic acid group. So dimethyl hexanoic acid. Okay. Now, so that's naming. Let's try drawing one. So in this one, you're asked to draw and name 2 different carboxylic acids that have the molecular formula C4H8O2. So the first one I would always say to do if you're given just a molecular formula and you need to try and draw different isomers, like we talked about when we did isomers, start out with the straight chain one because it's going to be easiest. So basically that means we're going to have, and it says that it's carboxylic acid, so we know we're going to have a carbon with our carboxyl group. So just like I said that you would be doing like the HOOC if you're starting from the left, we draw that in our structural formula as well. So H is always on the outside, whether it's on the left or on the right. So you should always be drawing this HO, not OH, and then bonded to the carbon with the double bonded oxygen. So now we have the end, and with carboxylic acid it always has to be at the end, so that makes it pretty easy to draw. And then we just have 4 carbons. So if this is our first one, we want to have 1, 2, 3, whoops. I don't want to put my dash in that early. 3 and 4. Yeah. Okay. So then the other thing we just need to think about is how do we fill in hydrogens? So this carbon has 1, 2, 3, 4 bond spots full. This carbon has 1, 2 spots full, which means it has 2 available. And same thing for this one because it's a mid chain. And then at the end, we're always going to have this CH3. Now that we've drawn it, we should always go back and just double check to make sure our numbers add up. So 2 oxygens we have, 8 hydrogens we have, 3, 5, 7, and 1 extra on that hydroxyl, so that's 8. And then the 4 carbons, 1, 2, 3, 4, so that's good. Now, if we want to draw another version of this, we want to start seeing if we can branch off. So remember that means you take 1 off of the main chain. So if we had 4 here to start, let's take this guy off the end and think about where we could put it. It can't be attached to this carbon because otherwise that's just the same structure. So it has to be attached to this carbon that comes right after the carboxylic acid. And it can't be attached to the carbon with the carboxylic acid because that already has 4 bonds. So the only option is to put it on carbon 2. So now we can just draw, it's going to be HO-C double bond O, and then it's going to go to a CH2, although we won't have space for the 2 because we're moving this branch off. So that's going to take the space of one of those hydrogens. So CH3, and then this one here now is going to have a freed up space, so it'll be CH3. Okay, so we have 1, 2, 3, 4 carbons. We have 3, 6, 7, 8 hydrogens and 2 oxygens. So we've met the criteria for that structure. Okay, so that's drawing carboxylic acids. Let's try one more. So this one's a little bit of a challenge. Technically, this has more functional groups than you are required to know, but being able to do kind of these challenge questions is still good because it just improves your confidence in knowing all of these naming rules. So in this one it says draw trichloroethanoic acid. So let's start out. We know that it's eth means there's going to be 2 carbons, and anoic acid means one of them is going to have, let's do it on this side this time, a double bonded oxygen and that hydroxyl group. So this carbon now has 1, 2, 3 bonds. We know there has to be a second carbon in the chain, so that's its 4th bond. For this carbon, it has the bond to a carbon, but now it has 3 available bond spaces. And we know that this was trichloro, so that means that there has to be 3 chlorines in this structure. They cannot attach to the carbon that is in the carboxyl group because it already is full in order to make the chain with the ethyl. So all 3 chloros have to be off of the second carbon. So let's just put that in there. So it'll be Cl, Cl, Cl. You could have also done like C, Cl3, C double bond O, OH. So that would have been all right too for the proper condensed structural formula. So this is a compound that's used for like chemical peels, if you've ever heard of that. You guys are all too young probably to need to worry about stuff like that. All right, so now I have a couple of practice problems for this. We're still going to go into esters so in this lesson, so make sure that you don't just totally quit out of the video. But if you want, you can pause the video, try these practice questions. I will go through them really quickly. If you feel like you get them, you can try and skip ahead to the esters really quickly if you just want to move on. So really quickly here, matching structural diagrams with their classifications. For an alcohol, we want to look for something that only has the OH group. So make sure you don't make the mistake of choosing this one that has that double bonded oxygen, just the hydroxyl group. Okay, so that's number 4. Aromatic, remember aromatics always have these benzene rings in them, so that has to be number 2. carboxylic acid has to have a carboxyl group, which is the double bonded O and the hydroxyl group. So that's going to be number 3. Halogenated hydrocarbon has to have a halogen in it. So that's fluorine, chlorine, bromine, or iodine. And only this one has chlorine in it. So number 2 again for that one. For practice number 2, we are given some different types of acids. Butanoic acid can be described as, so we see that it has this COOH group, so we know that it is a carboxylic acid. So that means that the functional group for it is a carboxyl, not an ester. We'll look at esters next, so that'll make more sense after that. So it's a carboxyl, so we know it has to be either C or A. And then we need to think about the first, is butanoic acid an aromatic or an aliphatic? So without anything to indicate that it's an aromatic, in which case it would have to have benzene in the name, right? So just remember, aromatic has to have that benzene ring. There's nothing in here that suggests that, and so we would list it as an aliphatic. Okay, so if you don't see benzene in the name, just make sure that you keep it as an aliphatic compound. Next one, we have practice number 3. We're given this structure of PABA, which is a component of sunscreen. PABA can be classified as now here we see the benzene ring, so that means it has to be aromatic, so it's either C or D. So it's an aromatic organic compound that is an alcohol or a carboxylic acid. So if we look at this functional group here, we have the alcohol group, but because we also have this carbonyl, together that's a carboxyl group, which makes it a carboxylic acid. So we want to choose D for that one. Okay, so those are all the practice questions for carboxylic acids, and now we're going to look at esters. So esters are hydrocarbon derivatives that contain something called an alkylated hydroxyl group. So basically what that means is when you have like an ester being formed, you actually have a carboxylic acid combining with an alcohol to make one compound. And so when we say alkylated hydroxyl group, this oxygen here was originally the OH group off of an alcohol. But we've taken off the hydrogen that would normally be there, and instead we've added an alkyl group, which is represented by this R2. R2 is just a variable that represents any carbon chain. So it could be one carbon with, 2 hydrogens attached, or 3 hydrogens attached. So it could be like CH3, or it could be like CH2 and then, another carbon, and it could go on indefinitely, right? However long that chain would be. So that's where the name alkylated hydroxyl group comes from. It's because originally this was a hydroxyl group, but we've replaced the hydrogen in the hydroxyl group and we've replaced that with an alkyl group, so some kind of hydrocarbon basically. Let's see. So alkylated hydroxyl group, remember just in the previous one with carboxylic acids, we talked about the carboxyl group, which was the C double bonded O and then OH, right? So that was carboxyl. This is alkylated hydroxyl, and some important things to be aware of with it is that this carbon double bonded to an oxygen has something attached off of it, which is represented by this variable R1. R1 can either be a hydrogen or it can be a carbon, like one or more carbons in a chain. Okay, so it could be CH whatever in however many you want basically there. But when we go off of, we have the double bonded oxygen, and then we also have off the same carbon a single bonded oxygen, and off of that oxygen you have to have a carbon group. Okay, and the reason for that is because if we had a hydrogen here, this whole group just becomes a carboxylic acid, right? This becomes a carboxyl group. So in order for it to be an ester, this component of the group has to be at least one carbon or more. Okay. In terms of physical properties, small esters usually have high solubility. So the same as we've seen with all the previous groups, if this is fairly small, like for example the carbon group coming off of here, then we're going to see high solubility because you don't have a extensive like coming off of here, you wouldn't have an extensive nonpolar component. So if this is fairly small, the fact that we have these polar oxygens, or like high electronegativity oxygens, means that there's going to be good solubility. But if that chain gets, like if either one of these chains actually becomes really long, then we end up having lower solubility. Okay, so that's pretty similar for the other compounds we've looked at. Interesting little thing in the news here, esters are associated with a lot of smells. And so one of the things that can help with is that esters, when bodies are decomposing, different types of bodies produce different types of esters, which are strong scent compounds. And so basically new research has shown that the compounds given off by decomposing remains distinguish humans and pigs from other animals. So 5 esters separate pigs and humans, and because there's these different compounds, the research can help police train dogs to detect human remains, right? Because they would want to make sure that they are identifying the esters that are associated with the decomposition of the human body. Okay, so like I just said, scents are strongly associated with esters. So again, in a test situation, often you'll be asked to identify physical property tests that you could do to identify what type of an organic compound you're working with. So for physical property tests with esters, a really good one is scent. Usually esters are going to have like fruity or floral or sweet aromas, okay? And so we can associate this a lot with like different types of fruit or flowers and the smells that we see with them. A lot of times esters are added to foods to enhance flavor. So if you ever see like any kind of additional flavor, especially for like fruit flavored things, often it's going to be esters that are responsible for that, and same thing with perfumes. Now in this picture here, we have aroma compounds in common flowers, and just like we did with the carboxylic acids, it's really good practice to be able to identify which of these compounds are esters. And then, I mean, the second question is just which flowers contain esters, which is just kind of for fun. But basically, the reason why I want you guys to be able to do this is because, like some students would look and say like, oh, there's a double bonded oxygen, that must be an ester. But keep in mind, same thing here, double bonded oxygen, but it's not an ester because off of that carbon, there's not a single bonded oxygen. Likewise, with a compound like this, you have a single bonded oxygen between carbons, but that neither of those carbons has a double bonded oxygen off of it, so it's still not an ester. If we look down here you have like an aromatic ring, and then going up to a carbon with a double bonded oxygen, and off of that same carbon is a single bonded oxygen, and off of that oxygen we see that there's going to be another carbon group, right? Because there's another line growing off of there. So that one would contain an ester group, like a functional group. If we go through these, double bonded oxygen, but no single. Same thing, no oxygens. This one here we can see has an alcohol group, but that's not really helpful. Same thing, another alcohol. But down here we can see, and even you can see in the name a little bit, I guess we haven't really looked at naming yet, but ethyl benzenoate. And so you see that there's the double bonded oxygen and the single bonded oxygen off of the same carbon. So that one also has an ester. And that's it. Those are the only ones with esters. So it doesn't really maybe make the best argument for the fact that the scent compounds come from esters, but those are just a couple of flowers. Same thing with mangoes here. So we can see in like some of the main compounds that are associated with the flavor of mangoes. In this one we have double bonded oxygen and a hydroxide. So think about, what does that mean? What kind of a group is that? That is a carboxylic acid, right? Because we have the double bonded oxygen. Oh, actually, Sorry guys, might cut out there. Actually, because this hydroxyl group is off of a separate carbon than the one with a double bonded oxygen, this is not a carboxylic acid. So this is nothing. This is an alcohol group here, but other than that, this isn't a functional group that we're working with in Chem 30. However, over here we have carbon with double bonded oxygen and single bonded oxygen, and we see the name, the familiar naming kind of style that we have for esters, which you guys will get to know in a minute. And same thing over here. This one might be kind of tricky because you have carbon with a double bonded oxygen and then a single bonded oxygen. No, that one works actually, because this carbon is bonded directly to the single bonded oxygen and the double bonded oxygen. So that one would also be an ester functional group. Okay. More kind of interesting, this is just some interesting news. There's a little bit of stuff about how the compounds that form from raspberries are actually able to form a gel that could be used to clean up oil spills, which is pretty cool, especially because it's obviously like natural compounds and probably not going to do a lot of damage in the environment. So kind of interesting there. Same thing here. They had this news piece about, is the galaxy raspberry flavored? Because they found, astronomers found that in the middle of the galaxy, there was, reasonably large quantities of this ester, which is ethyl formate, which is a component that contributes to the taste of raspberries. However, there's lots of other molecules that are detected, and in order to have the flavor of raspberries, there's a little bit of a more complex mixture of flavors than just this one component. And so, like they mention in here, it's probably a little bit romanticized to think that the center of the galaxy tastes like raspberries. Okay, so let's look at the functionality of naming and drawing esters. So an ester is made up out of two parts. Basically, it's a combination of a carboxylic acid and an alcohol. So if we want to see how the naming actually works here, we want to think about how an ester is made. So here you can see in the products we have the ester. We also have a water molecule. And in the reactants we have a carboxylic acid and an alcohol. So let's think about what the names are for these two components that are going to make up our product. So we have meth, eth, prop, and because it's a carboxylic acid, it's propanoic acid. Propanoic acid. For the alcohol, we have just the one carbon, so that's methanol. When we go to name our ester, first of all, let's look at what actually happens here. So we have CH3, CH2 carbon with a double bonded oxygen, then another oxygen, and then a CH3, and then nothing else on that chain, but we have a water separated. Maybe pause the video in a second and see if you can figure out what happened there, because if you can figure it out on your own, is going to be the best way for you to really understand it. Okay, so hopefully you did that, paused it, hopefully you figured it out, because basically it's just like putting together a puzzle. So if we look at what's happening here, CH3, CH2, carbon with a double bonded oxygen, and then in the ester structure we see that there's another oxygen, but instead of this hydrogen, we just have the CH3 from this group. So what could have happened? Well, if you think about, we have this hydrogen leaves, right? And we also have water as a product here. So water would be that hydrogen, but you also have a hydroxide group attached to that. So what's happening when these two things combine is this hydrogen is linking up with that hydroxide group to form water. And because that frees up this bond, now this CH3, this carbon, has one extra bond space, and this oxygen has one extra bond space, so they're going to link up, right? So you're going to have the oxygen and then the CH3 here. So when we name our ester, what we do is we use the names of the two parent molecules that made the ester. We always name the alcohol first and then the acid. So basically, we consider this to be the alkyl group. Remember how we talked about how this is an alkylated alkylated hydroxyl group. So this is the alkyl component, comes from the alcohol. So if there was only one carbon in the alcohol, it's a methyl group. So it's methyl. And then separately, we name the ester part. So if the ester part was 3 carbons, instead of naming it propanoic acid though, we change the ending, we cut off the oic acid and change it to propanoate. So it's methylpropanoate. Okay, and that's how these things are formed. Now later on we're going to look a little bit more in detail at how this actual reaction happens where we lose the water molecule, but you don't have to worry about that for now. So we have our acid component comes from the carbon that has the double bonded oxygen, and then whatever else comes off of there. Remember, this could just be a hydrogen over here, but with the alcohol component, you have the oxygen from the hydroxyl group, and then whatever carbon it was attached to. So actually, sorry, I guess I kind of misrepresented that here because I had the hydrogen being lost off the carboxylic acid, but actually it's more like this is bonding off to that hydrogen, and this oxygen stays on here from the alcohol. Okay, so this page goes over those rules again, but we kind of just did that, so I don't really see a lot of need to go over it again. Here, one of the things you might be asked to do as well is to identify the parents for different compounds. So if we look at this, just make sure that you can identify the first part is always the alcohol. So methyl is going to be this part, right? We have a single carbon over here. The carbon with the double bonded oxygen is always where you want to start counting for the acid component. Okay, and then the carbon on the other side of the single bonded oxygen is the one where you want to start counting for the alcohol. So our alcohol is methanol, right? So just changing it from methyl. And then this ethanoate shows that it's an ester, but the ester was built off of the alcohol and a carboxylic acid, so it would be ethanoic acid. Ethanoic acid. Same thing for this one. We have on the other side of the single bonded oxygen, so not the carbon with a double bond, we look and see there's 2 carbons, which means the alcohol was ethanol. And then the carbon with the double bonded oxygen is where we start counting for the carboxylic acid. So we have carbon 1, carbon 2, carbon 3 for prop. And because it's an acid, the parent of this part would have been propanoic acid. Okay. So there's one more example of this here. I accidentally forgot to remove the giveaway there, so I'll try to move this over so you guys can't see that. So if we look at this compound, we want to name the ester as well as the acid and alcohol from which it was prepared. So again, I kind of gave that away there. Oops. Let's see. So basically we would look at this chain, and after the oxygen you want to start counting. So there's 1 carbon here and then another carbon there. So that's 2. And remember that this component is always going to be your alcohol. So that would be ethanol. And then the carbon with your double bonded oxygen, that's carbon 1, carbon 2, carbon 3, and at the end here we have carbon 4. So that is bute. And if we were looking at this as the parent component, remember that would be a carboxylic acid, so that would be butanoic acid. Butanoic acid. And then if we put them together into the name of an ester, it's going to be ethyl. We change ethanol to ethyl. Butanoate. Okay, so our name is going to be ethyl butanoate. Okay, so that's how you find all of that. All the information is there on the filled out slide. we're going to get into more detail about how these reactions work a little bit later on, but it never hurts to start looking at them now. So basically what happens is you have, in order to make this reaction happen, you have a strong acid catalyst. So remember, a catalyst is something that makes the reaction happen without getting used up. It's used along with some heating to increase the rate of this reaction to make it kind of go along. Okay, let's try a couple more examples here. So naming the examples, we have a carbon here with a double bonded oxygen, and then off of that carbon, right to the, like not going to the single bonded oxygen, all we have is a hydrogen. So this is just a single carbon group that would have come from the acid component. So that would be methanoic acid. On the other side of the single bonded oxygen, we're going to have the alcohol. And so that's going to be 1 carbon, 2 carbon, 3 carbons. So that's propanol would be the parent alcohol. And so if we put that together, remember you want to name the alcohol first. So it's propyl. And then name the part that makes it the ester second, so that'd be propyl methanoate. These are probably the trickiest compounds that students really struggle with in Chem 30. So make sure that you spend a good amount of time on these esters because they're usually the place where most students mess up. And I'll just tell you now, there will be a written question with this, so make sure you know how to name esters. In this one here, fairly complex. So we have a carbon with a double bonded oxygen, single bonded oxygen. On the other side of that single bonded oxygen, we only have 1 carbon here. So that's going to come from our alcohol component. So that is going to be methanol. Okay. On the other side here, we're going to have carbon 1, carbon 2, 3, 4, or 3, 4, 5. We want to do the longest chain. So that means we have a side group for this one with 2 carbons, so it's going to be an ethyl group. Now the tricky part is if you ever have to name a side group off of an ester, you need to take into account which side it's branching off of. So because this is branching off of our our carboxylic acid component here, which is, let's see, pentanoic acid. Pentanoic acid. We name this component second, right? So it's going to be like methyl pentanoate. Because the branch is off of the pentanoate part, we put the number and the branch off of the second part of the name, not the first part. So when we name this, we would call it methyl. There's no side group off of that methyl, so we don't, identify this side group there. So methyl, and then just a space like we normally would have between methyl and pentanoate. But now we have to identify that on carbon 2. There's an ethyl group, so 2-ethyl pentanoate. Okay, so that's how we would name that one. So a little bit tricky because you have to identify the fact that the side group is off of the second component, the carboxylic acid component of the ester. All right, you guys, so that is everything for today. If you guys, I'm going to go through the practice really quickly, so if you want to see that, pause the video, do the practice yourself first, and then you can come back and check in on the answers. But if not, I will see you next time when we start looking at organic reactions, which, wow, good job there. And just make sure that you go in and do your practice problems out of the textbook. And if you want, you can always watch a video on hydrocarbon derivatives. Okay, but for now I'm going to go through the practice problems really quickly. So in this one it says an ester functional group is found in which compound? So with an ester, just keep in mind that means we need the double bonded oxygen and the single bonded oxygen. So in this one we have double bond but no single bond, so that one's out. In compound 2 we have double bonded oxygen, single bonded oxygen off of the same carbon, so that one would be in. Over here, same thing, carbon with a double bonded oxygen, single bonded. Oh, no, be careful. This is a hydrogen. So yeah, you do have to be careful with that one. With this one, the single bonded oxygen had another carbon off of it. So that's an ester. This one is a carboxylic acid. But if we look over here, we have carbon with a double bonded oxygen, a single bonded oxygen off of the same carbon, and then off of that oxygen is a proper functional group, not just a hydrogen. So that is also an ester functional group. On this one, we have single bonded oxygen, but there's no double bonded oxygen off of there. And the opposite here, we have a double bonded one, but no single bond off there. So the only ones we have are 2 and 3 having an ester group. Okay, again, so just identifying the class of molecule, carboxylic acid. So remember that's going to have the double bonded oxygen and the hydroxide group, so that should be number 2. For an aromatic, you have to see that benzene ring, so that's 6. For an alcohol, you just need the OH. Make sure that you don't have that double bonded oxygen because that makes it into a carboxylic acid, so number 1. For an ester, we need double bonded oxygen and a single bonded oxygen off that same one with an R group, not an H group off the end. So that'd be number 5. What is the name of the compound CH3CH2CH2 COOCH3? So with these, you always just have to be careful because it's like a condensed molecular formula, or sorry, expanded molecular formula actually. So with this one, you just have to make sure you can identify with this COO. This is the component where it's like that C would have a double bonded O, a single bonded O, and then the CH3. And then this CH2CH2CH3 is off of this direction. So when we're naming it, remember you're going to name the component to like the alcohol component from here first. So that would be 1 carbon is methyl. So it's either going to be B or C. And then off of the other side, we're going to have 1, 2, 3, 4 carbons. So that's butanoate. Now, a common mistake would be to mistake this for propanoate because a lot of students forget to include the carbon that has the double bonded oxygen and they just go 1, 2, 3. Make sure you're not making that mistake. This carbon still has to be counted even though it has kind of different bonds than we're used to seeing for carbons that we're counting. Chemicals which produce different flavors in fruits or fragrances in flowers belong to a class of hydrocarbon derivatives known as esters. There. Okay. We don't look at ethers. That's another good trick to know for tests. If you see a name that you don't recognize, don't wonder if you missed something. So ethers we never looked at. Aldehydes we also don't look at. And so the only other thing would be alcohols to choose from. And we know that those aren't responsible for like fruity scents and flavors. So esters would be the correct answer there. Let's see really quickly, matching. So ester, alcohol, carboxylic acid, and halogenated. So if we look at this first one, we just have an OH group, which we know is an alcohol. So that'd be 1. In this one, we have chlorine and fluorine, which are both halogens. So that would be halogenated hydrocarbon. In number 3, we have a bunch of carbons, then a carbon with these 2 oxygens, then another bunch of carbons. So that would be an ester. Versus this one where we have a bunch of carbons, the double oxygens, but on the other end is only a hydrogen. That's always going to be the carboxylic acid. So that would be number 4. This one here, what do we have? Matching structural formula with the compound name. Okay, so what do we have here? We have 1, 2, 3 carbons. Then we have that ester group and then another 3. So that would be propanoate. So that would be number 1. For this one, we have an double bonded oxygen but a hydroxide group, so we know that's going to be a carboxylic acid, meth, eth, prop. propanoic acid. So that'd be number 3. For this one, we just have the hydroxyl group, so that's an alcohol. So we're gonna see it end in OL, meth, eth, prop. So propan with the identification of that hydroxyl group. So that's 2. And last one, of course, we have a halogenated hydrocarbon. So that's going to be 1-chloropropane. So that's number 4 there. All right, that's everything. So you guys can go ahead and try your practice problems, and I will see you next time when we look at organic reactions.